Okay, so let's get started. Good morning, or yeah, it's still morning where you are. Good morning, class. Hope you had a restful semester break. We're about to start picking up from our conversation last class where we were talking about SN1, the SN1 products and the reaction itself. So let's see how far we can get today. And yeah, we're about to go. So our last conversation had us focusing on a specific reaction where we were looking at the product that results from SN1 attack. Now here we have a tertiary carbon electrophile that is being attacked by a neutral nucleophile in the form of water to give a racemic mixture of products. And in this case, the product is an alcohol. So this would be an example of what one calls a hydrolysis reaction. Hydrolysis because the product that results comes from the reaction of your electrophile with water. Okay? As you can see, your starting molecule is an alkyl chloride, and that is also significant because it's telling us that our electrophiles come in a number of forms. But the most important thing to keep an eye on is the fact that wherever you have an electrophile, your electrophilic carbon or your electrophilic center will have a delta plus, and your leaving group atom will have a delta minus. So that's one way that you can identify your electrophile on site. Okay, so right, so moving on, oh dear, let's go back. Right, so here we have our players identified, the electrophile, tertiary substituted carbon. It's good for SN1 reactions, as you know, and the reason for that is because SN1 reactions proceed by way of a carbocation intermediate. So of course, stability is important, and the stability of the carbocation increases as the substitution increases. Here is our nucleophile. It's a poor nucleophile. As I said before, it comes in the form of the water molecule. Here are our products, and here are our byproducts. So we're going to go through the reaction mechanism, and as we proceed through it, you'll get to see slowly how these products are formed and how your byproducts are formed. I want to give you guys a point of caution at this moment to let you understand that while our target would be the products that we're looking for in the reaction, it does not mean that we must ignore the byproducts that result. Although they may not be the primary focus of the reaction itself, they are important because they can lead to side reactions that reduce the yield of the products that you're looking for in the first place. All right, so starting with the first step in the SN1 reaction, we start with the loss of the leaving group. And there are things to note in our first step. First of all, for the SN1 reaction, we know that that step is the rate determining step. It is where the reaction takes its greatest length of time because it is the hardest step to accomplish. It is the step with the greatest activation barrier, and therefore it's the step that takes the most effort. Okay, now as you can see here, the chlorine would leave as a chloride. It is a weak conjugate base because it is the conjugate base of a strong acid, and that is what would make it a good leaving group, because as you know, poor bases make good leaving groups. Good bases make excellent nucleophiles. The step in this case is the slowest in the reaction mechanism. So then, as you can see, the electrons move from the bond onto the leaving group, indicating that that carbon-chlorine bond is breaking. And once it breaks, what we find is the formation of our carbocation intermediate plus the leaving group itself. So again, as you proceed through your mechanisms, make sure that you keep track of your byproducts. So in this case, your byproduct from this step is the chloride. It is true that you won't necessarily be using it, but you at least have to be attentive and aware of the fact that it is there. So our attack by the nucleophile is a fast step at this point, and one can understand why, because the carbocation that is formed is very unstable. And because it is unstable, in fact, its instability has a lot to do with the fact that the carbon is electron deficient. It is electron deficient in the sense that it has only 6 electrons surrounding it. Those 6 electrons show up in the form of 3 sigma bonds, right? So you have 1 here, 2 here, 3 here. This is your carbocation carbon. Of course, as we would have discussed in the previous session, this carbon has an empty p orbital. It is sp2 hybridized, but it has an empty p orbital, and that's where the electron deficiency is coming from. Alkenes are sp2 hybridized, but they are not electron deficient because they have an electron in those p orbitals. So here we have this unstable carbocation. The geometry is trigonal planar, as we've discussed already, so we're not going into that. But the instability that's coming from the electron deficiency of this intermediate is what causes it to be very non-discriminatory when it comes to reacting with nucleophiles. So really and truly, this carbocation is so deficient that it does not care what nucleophile it reacts with, just as long as it gets the electron deficiency matter addressed. So whether the nucleophile is strong or weak, it doesn't matter to the carbocation, as long as the nucleophile comes with electrons to supply that deficiency that the carbocation has. So that then means that the reaction is, this part of the reaction is very fast, and it occurs quickly, and therefore it's not rate determining. So the result of that attack would lead to our formation of a carbon oxygen bond, right, in the form of, in this case, our nucleophile is water. So the nucleophile attaches itself to the carbon center, and you can see the carbon now has 4 bonds, 1, 2, 3, 4, and it is now stable. It has now acquired the octet that it desired, that it needed, and so it's no longer reactive. However, we have a new issue. The issue here is that the oxygen came as a neutral, as part of a neutral molecule in the form of water. And so when it took one of its lone pairs to attack the carbon center in the carbocation, what that did is it forced the occurrence of a positive charge, a formal charge of +1 on the oxygen atom itself. So now the oxygen atom is unstable, and that has to be addressed. This would then be the formation of a second intermediate. So this was intermediate 1, and here is now intermediate 2 in this reaction in the form of an alkyl hydronium intermediate. Okay, so when you pay attention, when you look at this, you can see that your hydronium species looks very similar to water, and therefore you can also see that it looks similar to protonated water, and so that means it will have similar properties in that the reactions that protonated water can undergo would then be similar reactions that can apply in this case. And so, of course, that then means that the next step would be similar in terms of the acid-base reactivity that we are familiar with. We know water has the capacity to act as an acid as well as a base. But here's another thing that we need to be attentive to. The fact that you have this hydronium species present means that we have to address this quickly, because as it currently is, the hydronium form, or this intermediate here, presents water as a charged species. And when a species is charged in an electrophilic molecule, that particular species is also a good leaving group. So what that then means is we have to address the good leaving group nature of this highlighted molecule here and sort of attenuate the leaving group ability. We want to reduce the leaving group capacity of this molecule at the moment so that it doesn't revert. Because if it doesn't get attenuated, then we'll go right back to square one and we'll reform the carbocation, which defeats the purpose of the actual reaction in the first place. So then the next step makes sense in the sense that we have to now change our leaving group that is presently attached, that just recently attached itself to the carbocation. We now have to reduce that ability, minimize it so that it's not as good a leaving group as it currently is, so that the reaction can continue to proceed forward. And that is what we would then say is occurring in the form of deactivation. So we have to deactivate our leaving group, and we do that by neutralizing it. We neutralize our oxygen through the formation of, not through the formation, but through a deprotonation reaction, an acid-base reaction. So one can see that this is like H3O plus that can actually be equilibrated to H2O and H plus. Okay, so one can also envision a similar reaction occurring with our hydronium species by way of a deprotonation. Now there is a lot of water molecules present in this reaction, in the reaction medium, and so they can definitely perform this reaction for us to help to deactivate the water leaving group as it currently exists on this intermediate here. So of course that's what the next step will be, and that's the step that will afford us our deactivation of our leaving group. So water deprotonates the hydrogen, or removes the hydrogen from the hydronium species, pushing our electrons onto the oxygen atom itself. And what that then leads to is the formation of our alcohol product. And you note that once this alcohol product is formed, there is no longer the positive charge on the oxygen itself, and oxygen has reacquired its lone pair of electrons. So that now becomes the resting state for the reaction. The product has been formed, and we have our byproducts that have occurred as a result of this. So of course the chloride would have come from the first step, and the hydrogen, the H plus, would have come from the second step. And also we have water. So these would be our byproducts from this reaction. As well, of course, our product would have formed in racemic composition, right? Right, so in this scenario, what you've seen is that the overall reaction would have taken 3 steps. And the first step would have been the rate determining step. Now, when you consider the SN1 reaction, it's similar but different to the SN2 in that, of course, you have a substitution, that would be the similarity. The products would be similar in terms of the replacement of a leaving group with a nucleophile. But then the reaction conditions will slightly vary. And our electrophiles are also different. We've been discussing that, so you know that already. Our considerations remain the same. We have to give attention to what the electrophile is. We make sure that we keep track of our leaving groups, make sure that the leaving group is a good leaving group. If it isn't, then it has to be converted into a good leaving group before the reaction can occur. And so sometimes you will see that those steps are undertaken to ensure that reactivity can proceed. And of course, we're attentive to our nucleophile and our solvent. As opposed to the SN2 reaction, we just recognize that the nucleophile, in terms of its strength, is not significant for the SN1 reaction. The SN1 reaction actually is more dependent on the substitution of its electrophile and the strength or the ability of the leaving group. So essentially that first step for the SN1 reaction is really the critical step. All right. So our considerations, the process entails at least 2 steps. The first step is the slowest step. If the leaving group is poor, then an activation step will be necessary to convert it into a better one. If the nucleophile is weak, a deactivation step will be needed at the end to prevent it from leaving. We saw that with the water molecule. Water is a poor nucleophile because it's neutral and it really doesn't have, it has electrons, but the electrons wouldn't be as readily available as if you had a sodium hydroxide. And so at the end, it causes you to now have to get rid of that proton, which is the third step that we saw just now. Of course, the more intermediates there are, the more steps the mechanism will have. So let's take a look at our energy profile. We did so for the SN2 reaction, and so we can do so for the SN1 reaction. Don't be daunted by this picture. We're going to fill it in as we go and help you to identify the species so that you can be comfortable with what's happening. Of course, as you know, we would have been talking about intermediates and transition states and rate determining step and all of that. So where does that information come from? Well, as you can see on the picture before you, you have some labels and you have some energy humps, right? So to the left, we have the label R, which represents our starting material. And in this reaction, our starting material actually is the electrophile. That was the alkyl halide in this case. And of course, P represents the product. I1 and I2 represents our intermediates. And the first intermediate in this case is the carbocation, right? That's the first intermediate that was formed. It's a high energy intermediate. It's the highest energy intermediate, and therefore it's the one that will take the most energy to form, hence the rate determining step as we had identified before. The second intermediate, as you saw just a few moments ago, is the hydronium species, which results from having to now, having formed the product or the intermediate with a weak nucleophile, which then led to the need for a deprotonation. Of course, there is no intermediate that can form without first forming a transition state. So transition states 1, 2, and 3 represent those intermediary species that allow us to access the intermediate in the first place. So of course, transition state 1 would represent the carbocation being formed. So it would be an example like this, whereby we have our electrophile, and our electrophile has its bond being broken, but it is not fully broken yet. And so you can see the development of a partial negative charge on our leaving group, and the emergence of a partial positive charge on the electrophilic center. But it's not a full-blown carbocation yet. So this is what our transition state would look like in this case. Of course, there's an activation barrier for it as well, right? Because to get to the transition state, you have to climb uphill in energy. Even though the electrophile is reactive and it wants to substitute, it is, prior to that reaction, it is a situation where the carbon has a full octet. So the reaction proceeds uphill because you have to now break that, or you have to disrupt that harmony that exists prior, and that leads to what we call the activation barrier in terms of energy. Transition state 2, of course, if I were to draw my carbocation here, we already know that this is how it looks. So we have R2, R1, R3. All right, so now in going from our intermediate 1 to our intermediate 2, we also have, this is where our nucleophile is attacking. So it means then that we have a transition state that looks somewhat like the product, the intermediate product, but just not fully formed. So we draw dashed lines. Since our nucleophile is water, we will see that we begin to develop a partial plus charge on here. And there is still a partial plus charge here too. So this is what our transition state number 2 looks like. And then transition state number 3 is one where we are deprotonating. So we have R1, R3, R2, H, where this bond is being broken. It's not fully broken yet, but it is being broken. So this would be a delta plus on there. And of course, we know the product. Of course, we also know what this charged intermediate looks like because we saw it a few moments ago. R1, R2. Okay, let me just fix that. One, two. So this is our charged intermediate here. And of course, we know our product. Right? So let's clear that. So here, of course, for every transition state, there is a corresponding activation barrier, and that's where you see that highlighted in the various spaces. We have three of them, three different activation barriers, and you can see the first one going from the electrophile to the carbocation is the largest activation barrier. Okay, so that then makes sense as to why that would then be the first step. Sorry, not why that's the first step, but why that would be the rate determining step, because it is the one with the largest activation energy, hence it is the slowest. The second step is a fast step, as well as the third step. Activation barriers are low for those, hence the rate constants are low for those. Okay, good. So moving forward, we can then see that the rate law for this reaction is actually determined by the rate constant and the electrophile itself. So unlike the SN2 reaction, where your rate was determined by the concentration of your nucleophile and your electrophile, the SN1 reaction is different in that our rate is determined by the concentration of the electrophile alone. Of course, we see why in that first step, the only species that is reacting is the electrophile. The nucleophile is not involved in that step. And so it being the slowest step makes it the rate determining step, but it also says that that step does not include any other species except the electrophile itself. And so it's important for you guys to be attentive to that, because that's a distinguishing feature, or one of the distinguishing features that separates the SN1 mechanism from the SN2. All right, so revisiting our reaction, we just did that a few moments ago, but we're able to now put the two pieces together, and we're able to see that our electrophile represents R, it's at one energy level. The intermediate one represents our carbocation, which is at a higher energy level. Then as the reaction progresses, we get to the hydronium species. It is lower in energy than our carbocation and at times our electrophile. And of course, finally, our product is the substitution product. And it is expected that it will be at a stable enough state that it is energetically accessible. Now, I want to point something out to you guys. Here, it is not always going to be the case that your product is at a lower energy level than your starting material. In this case, it is, and that suggests that what you have is an exothermic reaction. There are going to be scenarios where your product is going to be at a higher energy level than your starting material. Those would be scenarios where the reaction is endothermic. Okay? All right, so moving forward, let's just summarize that. We have our steps. Step 1 is the formation of the carbocation intermediate, as is demonstrated on the energy profile here. Step 2 is the formation of your hydronium species. Step 3 is the formation of the product. As you can see, those two subsequent steps are pretty fast, and they're pretty much downhill in energy. All right, so what are some of the best SN1 electrophiles? SN1 electrophiles come in many shapes and sizes, of course, but the general trend is that our electrophiles have to be seen in the light of the intermediate that they will form. So it then means that since we know that the critical intermediate in an SN1 reaction is a carbocation, we have to look at our electrophiles through the lens of what kind of carbocation would form as a result of it, or resulting from it, right? So in the case of the first electrophile, we have a simple alkyl carbocation, a simple alkyl electrophile, which would lead to a simple alkyl carbocation. And so we see that here, where our carbon center is positively charged, and you have three substituents, three alkyl substituents. We have the methyl groups, and this is what we would call a tertiary substituted electrophile. Of course, the precursor would be with your leaving group, whatever your leaving group is. So you'd have your R group. One, two, and three. And of course, when we say R, we mean not hydrogen. So this is your typical electrophile for SN1, one of the best ones. And of course, when you compare it to the other option, which is here, so this is a tertiary substituted electrophile. And what you have here before you is the result of a secondary substituted electrophile. It's not as efficient for SN1 reactions because the substitution is less, which means that the carbocation is less stabilized. So here we have a precursor that would come in the form of HR1, R2. Not as stable. Secondary substituted. Okay. Then we have a second category of electrophiles known as the conjugated group. And these are what you call your allylic or your benzylic groups. So here, these are your electrophiles that result from a double bond that is adjacent to the carbon that has your leaving group. So this is your carbon that has your leaving group. And here is your leaving group, obviously. And then adjacent to that is a pi system, an alkene. So why is this considered a stable electrophile for SN1? Well, remember a few moments ago, I mentioned to you that the carbocation is electron deficient. It is sp2 hybridized, but it is electron deficient because there are no electrons in that p orbital. Well, here we have sp2 hybridized carbons as well that result from the alkene, right? But these sp2 hybridized carbon atoms have p orbitals that contain electrons. And so if you form a carbocation from this molecule by way of the leaving group departing, even though your carbocation is electron deficient, it can borrow electron density from this pi system here. It can borrow electrons from the neighboring alkene. And so that is what causes this particular set of electrophiles to be stabilized. So even though this is what we can see this is a primary carbocation, primary carbocations are not favored in SN1 reactions at all. However, if a primary carbocation exists in the presence of an allylic system, then the reaction will occur. And it's for this reason that I am presenting to you guys that is possible. In a similar situation, we have that recurring with the benzylic carbocation. So here is the benzylic carbocation that shows us a pi system. In this case, it is 6 p orbitals that contain 6 pi electrons. And these 6 pi electrons can travel around and donate electron density to the empty p orbital that's on our carbocation. Yeah, let's tidy that up. So this one is electron deficient, but this pi system here contains 6 pi electrons that is able to lend electrons over to the carbocation center itself. All right. So again, in this situation, you have a primary carbocation, but it is stabilized by the presence of a pi system. And that's what we look, when we say it's conjugated, that's what we mean. So here now, our third category are our heteroatom stabilized carbocations. So let's say we have an electrophile that is bonded to a leaving group, but it also has a heteroatom, meaning an electronegative element on it. And you see these all the time. You see these especially in the glycosidic bonds systems, where you have carbohydrates. They oftentimes have molecular structures that appear like this. So we have CH3O in this case. And let's say this is, just put a random leaving group, H. Of course, the oxygen has 2 pairs of electrons. So the electrons on the oxygen actually help to push out our leaving group. And when it does that, it actually, the lone pair electrons collapse onto the oxygen carbon bond. And that forces our leaving group, which is already a good leaving group, to leave. And this is the result. So it is sort of as if the oxygen is lending its electrons to the carbocation carbon. And so you have these 2 canonical structures here in terms of resonance that lead to what we call stabilized oxonium ions. It's not just limited to oxygen. You can see this happening with nitrogen as well. And so here are your scenarios. So you have 3 main categories of carbocations that result from various SN1 electrophiles. All right? So electrophiles that form stable carbocations readily react by SN1. And our stable carbocations come in at least 3 categories. One of them is the alkyl group, the alkyl stabilized carbocations. We have our conjugated carbocations, and then we have our heteroatom stabilized carbocations. The reactivity of our SN1 and SN2 reactions, our SN1 and SN2 electrophiles vary depending on the electrophile that you're interacting with. So at the top you can see that we have a number of them, but what we see is that at the top we have a primary alkyl halide, which comes in the form of propyl chloride, right? This is likely to be SN2, as you see on the table. Then you have a secondary alkyl halide, likely to be SN2 as well. I mean, it can go by way of SN1, but either one, it may be more preferred for it to go SN2. The ones that are highlighted in pink are your tertiary carbocations or your tertiary electrophiles, as well as your allylic and your benzylic stabilized allylic carbocation or electrophile. And the numbers hold true. You can see that they are actually increasing as we go up. So in the case of the last two, where you have 130,000 units in terms of rate, you can see that the allylic cation is tertiary at one end, but it actually is stabilized because it is tertiary. In the case of the second one, you have an allylic carbocation, but it is not tertiary. It is primary. So that reduces the rate at which it can react. It still reacts fast compared to the tert butyl chloride that you see at the top here. It still is a fast reaction compared to this guy, but it is not as fast as this one. And that's because substitution does matter at the end. Okay. I think I am 1 minute over my time, so this will be a good place for me to stop. We will pick this up tomorrow. Not tomorrow, sorry. I know tomorrow is a holiday. We'll pick this up on Friday, and hopefully we can wrap up SN1 and SN2 by the end of this week. Okay, guys, I am going to release you now, and I hope that you have a good day. We will reconvene for lab. You will be able to see what we're doing for lab today once you join. Until such time, be safe and have a good afternoon. Okay? Take care, guys.
Hey,
For
Miss.
those of you that stay on, we can work some questions, no problem. I'm going to stop sharing my screen.
Miss, for our assignment.
Yes, assignment. Stop recording. So just 1 second, let me stop this.